make sure that it is in fact including the voice. Okay. Come on. Uh-oh. Just lost my cursor. Okay, there we go. So it is streaming, but this is not the actual screen. I bet. All right, so we got it fixed here. Nope, no. No, do not exit. Just minimize. There we go. Okay.
I do that all the time. And it doesn't give me warnings.
Oh, did you turn off those warnings?
Wow. In other texts. All over the place. I want to do that, you know.
All right. So this is the a practice exam, okay, which is based on the actual exam last semester. So ignore the date. It's not going to be the same date. It's 1 week from today. So today is the 25th, and I think it's going to be October 2nd that we are going to have our exam. Room number changed. It's going to be here during the lecture time. This part is not changed. It is definitely open book and open notes, which means everything that you can print or handwrite prior to the test, you can bring. Everything that you can purchase online, you can bring too. If you can find someone who has spent the time to compile every single test that I have ever administered for this class, you can get a copy of that and bring it with you. That's okay too, not a problem. I mean, many of those are recorded. I do exam review after every single one. So if you look up, if you look up like 2 days after the 16th of March, you will find the review session of this particular test. Okay, and you can watch that video if you want to, take screenshots and bring it with you. Not a problem. If you find certain textbooks that you find is really helpful to explain what is carry look ahead and that sort of thing, bring it with you. Just remember, the more stuff you bring, the more difficult it is to look for something in that pile of stuff that you brought along, that you will be bringing along. So I would suggest that you find a way to index so that you can find things easier. Okay. The test is individual, okay, which means the score of a particular person should only indicate the knowledge and competency of that person and not of anyone else. Okay. And all the rules should be followed. In other words, it's open book and open notes, but clearly no electronics. If you want to bring a scientific calculator, go ahead and bring one, okay? If you want to bring a scientific calculator that has base conversion and can deal with binary numbers, that's okay too. I pretty much make sure that I ask questions that cannot be done easily using a calculator, even if it can do binary numbers. So if you have a calculator that can do binary numbers and hexadecimal numbers, hey, not a problem. You can bring that along. But you cannot use a cell phone, you cannot use a tablet, you cannot use laptop computers, you cannot have communication with outside using Bluetooth or near field communication, IR, or any other means. You might want to bring additional sheets of paper because some people are known to write down the answer and then they just cross out the entire answer and then they need some other space to write the alternative or the revised answer. You want to write legibly. I cannot tell you how many times I cannot figure out, okay, what is this squiggly doing here? You also want to understand that questions do not necessarily have equal weight, which means when you evaluate which question you want to tackle first, you might want to take into consideration both the difficulty level of the question as well as how many points it's carrying. Okay. My personal preference is really just take a quick glance of all the questions, find out which one is easiest. Okay, even if it's just a 2 point out of however number of points, if it's easy, do it first. So tackle all the easy ones first and then leave the more difficult questions to later. So this way, if you do run out of time, then you would have captured every single point that you could have captured because you do all the easy ones first. If you do the difficult ones first, even if it carries a lot of points, you may run out of time. Then you will basically have left some questions that you could have answered for sure to get some points, and you will not have time to do it. I will give you the number of questions. It may or may not be 6. Okay, and this exam will account for 20% of your final grade. So, are there any questions at this point about all of this stuff here? Questions? All right, so you will see some questions crossed out because I have said that this class will only have the exam material up to and including double conversion. So this is about memory devices. We're not gonna have that question. This one is based on the previous question. Once again, we're gonna throw that out. This question is here. Okay, so what we'll do is we'll take a look at it. The answer is already here, but I can explain that. So question number 3 requires you to kind of remember or look up in your notes, what is binary subtraction. And the real question is separated into 3 parts. So we use the result. I even give you what the result function looks like and also what the borrow function looks like. In a borrow look-ahead subtractor, okay. In a borrow look-ahead subtractor, the bit bi can be recursively defined as this. Have we seen this somewhere before? I think we have seen it several times. The first time is in the adder, and then the second time is in the subtractor. But the structure is the same. So the first thing is, what are the terms gi and pi to make this recursive definition work? Well, that's part of the notes. Gi is the negation of xi conjunction with yi. Pi is the negation of xi disjunction with yi. Is that okay so far with the answer itself? Okay. So these are things that you can just kind of look up. Part B, using the recursive definition, derive, okay, so you might want to look at what I'm asking you to do. Derive and spell out B2 step by step by expanding the BI terms one by one. So B2, by definition, is this part here. That is based on this definition here. You don't even have to look it up. It's already here. Is that part okay? How B2 is expanded to G1 plus B1, P1, B1. It's because of this. I, in this case, is 2. 2 minus 1 is 1, and that's why we got G1 itself. And then we also have 2 minus 1, which is 1, which is P1, and also B1. But B1 itself is recursive, which means it can be expanded. So B1 itself, which is this part here, is expanded to the content inside this pair of parentheses, which is G0 plus P0, B0. And then when you distribute this, you get G1 plus G0, P1 plus P0, P1, B0. And remember, addition is not addition. Addition is disjunction. And multiplication is not multiplication. It is conjunction. So do we have any questions about the question of part B or the answer to that part? No questions? Okay. So in a question like this, if the middle part, like this part, is missing entirely, that answer will probably get no points or a very low point. Because the idea is I need to know whether you understand how it is defined and how to expand it. This one can be found in the notes. You can just copy and paste it from the note, which is not what I'm asking. I'm asking, do you know how we got to that? Okay, so part C is a little bit more complicated. You might want to draw pictures if you need to. Assuming that we only have AND or OR gates that only have 2 inputs, so we have a restriction here, which is not in your homework assignment. Because in your homework assignment, when you were working on your borrowed look-ahead subtractor, you can use AND gates and OR gates with any number of inputs. But in this case, we are limiting only to 2 inputs. The question is, how many gates in total do we need in order to compute B2? In order to implement this equation, this expression, how many gates do we need when each gate only has 2 inputs? Derive your answer step by step and explain the rationale. So a picture can be very useful because you can just show me the schematic of the circuit diagram, or you can just kind of explain it in words. Okay, you can just explain that G1 is going to take up 1 gate, it's taking up 1 AND gate, G0 will take up another AND gate, P1 will take up another OR gate, and then P0 will take up another OR gate. So just to compute the G terms and the P terms, we need 4 gates in total already. Is that part okay? Because we are starting with something that is known. The only thing you know that is given to you are the X, the Y's, and also B0. Those are the input pins. Everything else you have to compute. And then the second part is to say, okay, now that we have the G's and the P's, how many gates do we need to compute this? Well, this is one problem because we have 3 items in a conjunction and we cannot have a 3 input AND gate. So how do you separate a 3 input like this into several AND gates? So the answer is, well, you can always group 2 like this into 1 AND gate, take the output of this AND gate, feed it to the next one, which will combine P0 and the output of the previous AND gate. So that takes up 2 gates right there. This one takes up exactly 1 AND gate. So now we have 3 AND gates. But the disjunction is the same way. We cannot have a 3 input disjunction. We can only have 2 input disjunctions. So you can group these 2 to use 1 OR gate. So that will make 4 gates. And then have another OR gate overall. So now we need 5 gates. So this part takes 3 AND 2 gates and 2 OR 2 gates. The first part takes 2 AND 2 gates, 2 OR 2 gates. So the total adds up to 9. Do we have any questions about that? We need 9 gates in order to implement this logic here. Yep.
So for explain the rationale, is that enough, or do you want us to write out some sort of?
This would be enough, just by grouping the parentheses. This is sufficient.
That's enough.
It is sufficient because when I look into each parentheses or when I look into each operator, it only has 2 sides. So that is enough implication. But you do have to summarize that because of that, we end up with 3 AND gates and 2 OR gates.
And then do you want the overall summary?
Yeah, 9 gates. Yeah, a total of 9 is needed. Yep. So I kind of forgot to put that here. If you work up to this point, I'm not going to take any points off if someone just forget to say, oh, we need a total of 9 gates. Yep.
Would you accept the diagram as an answer?
I will accept the diagram as an answer as long as when I count the gates, it adds up to 92. But the diagram also has to be correct. It cannot just be like 9 gates that kind of randomly scattered over the thing. So it has to be connected correctly to reflect that expression.
Or to label the gates as well? Or to label the gates as well?
No, you do not. But you do need to indicate which one connects where. So that in the end, the diagram has to show that it does implement this particular expression. Is that okay? All right. Okay. Question number 4 is crossed out because it is asking about something that we have not talked about, which is the RAM module. So we will skip that. Question number 5 is also skipped because it talks about the microcode engine that we haven't really talked about. No, this one is about binary addition. Oh, I should not have crossed this out. Oh. Okay, let's uncross out this one. Yep, this one should not be crossed out because we did talk about addition, we talked about comparison, and this one is about comparison. Okay. So complete the following long binary addition, specify all the carry bits as well as result bits. So the ones that are here are given to you. We are adding 0, 1, 1, 0 to 0, 0, 1, 1. I want to know what goes into this row. These are the carries. And for the carries, you need to indicate the overall carry as well. And then this is the actual answer, which is the sum. Okay, so let's work on this one. 0 plus 1 is 1. And then 1 plus 0 is 1. And neither addition results in a carry. So there's a carry of 0 from the first column. 1 plus 1 is a 0, but that gives me a carry to the next one already. 0 plus 0 is a 0. There we go. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. 0 plus 1 is a 1. And we have an overall carry of 0 as a result. So that is what I'm expecting. The bottom row itself is not important. Okay, so if it does carry points, it's not going to be a whole lot. It is the rows in between that is important. Is that okay? Because anyone with a calculator that can do binary numbers can figure out the last row, but not the ones in between.
Professor?
Okay. Yep.
If we're to do addition, but with signed numbers, how would you indicate that?
Indicate
in the table, the sign number.
The sign number.
Yes. Would
Well,
it
this
be
okay.
part of the plus 0, or would it be underneath one of the actual columns?
But the mechanism of adding and subtracting does not matter whether the values represented are signed or not. The mechanism of adding and subtracting, which can be implemented using logic gates, has nothing to do with your choice of should I interpret the bit patterns as signed numbers or unsigned numbers. So that part really should not matter. Okay? Okay, but that's not the end of it. Okay, but there's more. So what we also need to indicate would be the overall carry, the 0 flag. Did we talk about the 0 flag in this class? No? Okay. So cross that out. Because this is based on the notes still on Moodle, but I'm transitioning to Canvas right now. But we did talk about all of these other flags. Okay, the Z flag is the only one that we haven't talked about. So what about the overall carry in this case? 0. It's a 0 because the overall carry is this flag here. So that's a 0. What about the overall sign of this number? The sign flag is the most significant bit of the result. 1. It's a 1. Yep, it is because of this one here. Okay, what about overflow? So this is addition. We haven't really talked about, well, we talked about it a little bit, but we didn't actually finish the discussion. So if you look at the sign of the result, does it make sense? Okay, the numbers that we're adding, if we are to look at the first 2 rows as signed numbers, are they negative or are they non-negative? They're non-negative, very good. Okay, what about the sum? The sum is negative. So when you're adding 2 non-negative numbers, but you end up with a negative sum, does the sign of the sum make sense? No. So do we have an overflow condition? Yes. Okay. And then the L flag is the exclusive OR between the sign and the overflow flag, which in this case is asking, are they different? Is the sign flag and the overflow flag different? That's the definition of the L flag. They're not different. So that means the L flag is a 0. Yep.
Can we explain the O flag again?
The overflow flag for addition, for subtraction or addition, simply means that if the sign of the result does not make sense, then the overflow flag is going to be a 1 to indicate that we have an overflow condition. So in this case, because we're adding 2 non-negative values, but we end up with a negative sum, that's why the sign is, that's why the overflow is a 1, because the sign of the sum does not make sense. Yep.
So if the sign flag and the overflow flag are different, would
the L flag would be a 1.
It would be a 1.
Yes.
Okay.
If one is a 1, the other one is a 0, doesn't matter which one is 1 or which one is a 0, then the L flag is going to be a 1.
And
Yep.
if they were both,
if they are the same, then the L flag is 0. Doesn't matter whether both 1s or both 0s,
okay.
the L flag would still be a 0 in that case. Yep. Yep.
Why is the L flag significant?
It is not in this case, but since the L flag is really just the exclusive OR between the sign and the overflow, it still has a value. It's just that we probably won't be using it for anything. Okay. Yep.
How is the overflow used?
The overflow flag being a 1 indicates that the addition ends up with a value that we cannot represent using the number of bits that are allocated. So it can be used to indicate a condition. It can be, for instance, if you are using a programming language where when you try to store the result of a calculation and it is out of range, it should throw an exception. This will trigger the throwing of the exception. Unfortunately, C and C++ do not care. So you can overflow and it will just store the result. It will just store the bit pattern, but it won't give you an indication that you have a problem. But other programming languages like Visual Basic and some other scripting languages, when you perform a calculation and then the result of the calculation cannot be represented using the same number of bits, it will actually cause an exception. So it will just stop the execution of the whole program, which is the proper behavior because you might want to know about it. Okay, is that okay so far? Yep, go ahead.
One more clarification.
Yeah, go ahead.
Okay, so if the two numbers we were adding together both started with 1s, but the result ended up with 0, what would the overflow flag be? Would it be the 0, or would it be 1 in this
Okay.
case? Correct.
Those are good questions. So instead of doing that, let me just name this bit as A, name this bit as B, and name this bit as C. Okay. So in an addition, the overflow flag would be having the two numbers that you're adding having one particular sign, but the result of some having a different sign. So in this case, one way to make it fail is to have AB not C. AB not C means that A is a 1, B is a 1, but C is a 0. So you're adding two negative values, but you somehow end up with a non-negative sum. The sum doesn't make any sense. Okay? But there's another way to fail to have an overflow condition, which is not A, not B, C. Not A means A is a 0, not B means B is a 0, and C means C is a 1, which is exactly what we have in this particular case. So that is overflow as well. But this only applies to addition. The equation for subtraction is different.
So basically, if the sign is what we're not expecting, overflow is going to equal 1 regardless of...
That is correct.
Okay.
Because overflow is basically just pointing to the sign and saying, he's wrong.
Okay.
Yep.
Overflow, since you keep on saying sign, does overflow just apply for sign numbers? Or do you have to indicate
That is a good question. Okay, so by definition, this is how we can calculate overflow for addition. The overflow for subtraction is in the notes, so you got that one already, okay? But if you look at this equation, it has nothing to do with the interpretation of the bits. It's simply saying, okay, is A a 1? Okay, is B a 1? Is C a 0? Oh, if that is the case, we have overflow. So you're not really caring about whether you're interpreting the numbers as signed or unsigned. In other words, whenever you do addition, this happens. Whenever you do subtraction, the other equation applies. But you still have a overflow result, you still have a sign flag, you still have an L flag, you still have a carry flag. But we are not paying attention to any one of those. We are setting those, we are changing them, but we are not using them. So when you use which flag depends then on what is the correct interpretation of the bit patterns. But the only time you need to do that is when you're about to branch, when you're about to say, if this number is less than that number, let's go that way. That is the time that you have to choose which one of these flags should you look at in order to make that decision. But since we haven't really talked about branching, so at this point, it doesn't really matter. We just set these flags, because they're all going to be set regardless. So the calculation, addition and subtraction, will set all of these flags. You know, there's one extra flag called the Z flag, but since we haven't talked about it, we're not going to talk about it here. But these 4 flags that we have talked about so far, they will be set after each subtraction and after each addition. But since they're only stored somewhere in the processor, and we haven't really talked about how to make use of these flags, so at this point, you know, we don't really need to know, you know, well, why would we want to compute this one? Well, you know, because it's not at this point that we pay attention to the flags. Is that okay? All right, cool. Question 6 is definitely crossed out unless you guys want to take on this challenge. Okay, definitely gone. And that's why we have some additional questions later on. Okay, question number 7 is an additional question. Assuming that we can use 2 input exclusive OR gates to make things simpler, we can use regular AND gates, conjunction, we can use regular OR gates, disjunction, and we can also use those particular gates with optionally negated inputs, the bubble, you know, for the inputs. What is the total number of gates to propagate through in a 3-bit carry look-ahead adder that has an overall carry bit? So we want to figure out, you know, in order for the sum and also for the overall carry bit to settle, to have the correct value, how many propagations do we have to go through? How many levels of propagation do we have to go through in order for the entire result to be ready? So the first thing we need to do, I need to do, is to make sure that you guys understand what the question is asking. So assuming that each gate, like an OR gate, takes a certain amount of time from the amount of time that the input is valid to the time that the output is valid, there's a certain latency, okay? So I'm asking how many latencies are we talking about? I'm not talking about the absolute time, I'm just talking about how many gates do we have to go through in order for the result to be valid. Right? So to answer this question, I think it's really best to use the document camera so I can actually draw the picture. So this way you guys can see, and it would be a good idea for you to draw the picture too in the exam, so that, you know, if you don't have time to summarize, your picture will at least give me an idea that yes, you're on the right track, you can get partial credit for that. So there are partial credit in the test. You know, when I grade, I try not to be binary when I'm grading, even though this class is all about binary stuff. So I will try to give partial credit depending on, do I see evidence that somebody has understanding of the material that I'm really testing. So let me set this up, and then we can go from here. But do we have any questions about the question itself? Does everybody understand what I'm asking? Okay, all right. And I got everything moved to the wrong place, so I have to move everything back here. And let's see, we can maximize this. Okay. Okay. Yep, you guys can definitely see my Band-Aid with a camel extra piece of tape on top. Because if I don't put extra pressure on it, the blood would actually ooze out of the Band-Aid itself.
You do like the liquid scab thing?
Those will work, but only if you can, you know, only if there's no bleeding, there's no pressure, you know, pushing out.
Are you sure you don't need stitches?
Not anymore. Yeah, but keeping the pressure on, you know, I think it will heal itself. We'll give it a few days. Yeah, if I lose a few cc of blood each day, I will still be okay. All right, so let's go back to that question. It is this one. We want to figure out So everything is 2 input, okay? Exclusive OR, 2 input, OR, 2 input, and 2 input, and so on. And we are talking about the 3-bit carry look-ahead adder. All right, so how do we solve this problem? First thing is to look up the equation, right? And you can probably just kind of focus on the most difficult ones and not so much on the ones that are kind of like, those are easy. Because the easy ones, do not have a whole lot of propagations. So we want to go back to binary number addition, which is the node that contains the K3, which is the one that is the more complicated. So you go to section 6, and then you just look up what is K3, which is already computed and presented here. So we focus on this one first, okay, and figure out, okay, so how do we do this using only 2 input gates, but we want to do it as quickly as we can. Is that okay? All right. So you look at this, and let's say the number of gates is not a problem. It's the level that is the issue. Okay, how many levels do we have to go through? So when you look at this, okay, I need to display both at the same time. So let me put this one all the way to the top here, and then resize this one so that we can kind of superimpose, not superimpose, but we can look at both at the same time. There we go. All right, there we go. All right, so what we can do to make this as quickly as possible is to have K0, P0, using one AND gate, okay? And then we can have P1, P2 using another AND gate. P1, P2 going into another AND gate. But because the last term here is involving the conjunction of those 2, so we have another AND gate here to compute the last term. The second last term has 3 things, but one thing is already pre-computed. So that means, I just really need G0, and we tap this one from here, and then just feed G0 into this one, and then we have the second term. This is the second last term, which has 4 items in it. This is the, excuse me, this is the last term that has 4 items. This is the second last item, which has 3, the second last term, which has 3 items. Is that okay? In other words, this one is computing P2, P1, P0, K0. This one is now computing P2, P1, G0. And then we are left with P2, G1. Okay, so we can have another gate here. P2 goes here, and then G1 goes here. And then we have G2 all by itself. It doesn't need to go through any gates. So when these 4 signals are available, okay, we can group these 2 into one single OR gate. Remember, the OR gates are also limited to only 2 inputs. So that will, so this gate is computing these 2. This gate is computing the disjunction between these 2. So we need one overall disjunction to combine the smaller results of the disjunctions into one single actual output, which is our K3. So are we okay with this one? But this is assuming that we start with P0 and P1, P2, and all the P terms, which means there's one additional level of gates prior to this. Because P0 is an OR gate itself, P1, P2, those are all OR gates. The G terms are all AND gates. So now when you look at the number of level of gates that we have to go through, this is the first level. This is the second level. Now we can number, this one as a second level too. Okay. This is a third level. This is a fourth level. And this is a fifth level. So it will take at least 5 propagational delays in order to go from the individual X bits and Y bits to K3. Okay. Well, fortunately, K3 is not used in the sum because it is just dangling on its own, being the most significant bit carry. But K2 unfortunately has to be used. So now we have 5. So in the next picture, we want to look at the other K, which is K2, and we want to figure out, combining K2 with the exclusive OR to calculate the sum. How many gates do we need in that case? Because we don't know yet, which one is going to take the longer delay. So in this case, we have P. Okay, so let's do the first level first. Okay, so we have OR gates to compute P0, OR gate to compute P1, and K0 is given already, so K0 doesn't need any computation. So now we have these 3. In order to make a conjunction, you need to have one conjunction to combine these 2, another conjunction here to take the output of the first conjunction, and then take one of the signals from the second one. Let me see if there's a faster way to do this. I think there's a faster way to do it. Okay, so let me do this one more time. This is P0, and this is P1, and we'll group K0. Nope, there's no faster way to do it. Sorry, take it back. Okay, so this output is corresponding to this one here. Now we need to figure out what is P1G0. P1 is already here, and then G0 is the result of an AND gate. So these 2 combine using an AND gate. That becomes the middle term. And then we have G1 all by itself, which does not require any gates, well, other than the AND gate. Then we have these 3, we need disjunctions. And there's no quick way to do it. We can combine these 2 first. Okay, this is the slightly faster way. And then take the output of the first disjunction, merge, combine it with the output of the other term to have the final result, and this is going to be K2. Are there any questions about this part? No questions? Okay. So how many levels are we talking about already at this point? We got the first level. Okay, let me use a different color pen here. So we got all of these as our first level gates. Okay, there's no way around these things being the first level because they first have to be computed first. And the second level ones will be the ones that depend on the output of these guys. So we have this one being the second level, and also this one being the second level. This is also first level, by the way. There you go. So first level, second level. Then we look for gates that depend on the output of the second level gates. This one is third level. This one is third level as well. And then we look at the fourth level gate, which is this one here. So are we doing okay so far labeling, the stages? Is that okay? But K2 is not the final answer that we need, because K2 needs to be combined with xy, x1, x2, y2 in order to come up with the actual sum. You remember that? Okay. So at this point, x2, y2, we can use an exclusive OR gate for these 2 and pre-compute that while we are doing the rest. So this one will still be a first level gate. But by the time we have the output coming out of this one here, we need another exclusive OR to take this one and also the carry bit in order to come up with the sum bit, or bit 2 of the sum. So that means, by the time we get to this exclusive OR, it's going to be the 5th level. So once again, if we have 5 levels of gate propagation to get to bit 2 of the sum, just like K3. So they are equally slow. That means that the entire adder will take 5 gate propagations. Are we doing okay so far with that calculation? Now, once again, if you want to waste silicon and you recompute your P1 somewhere else, instead of tapping it here, and you just have another P2 OR gate P1 OR gate to calculate it, that's fine, okay? Because it's not adding any additional levels of propagation. It's just wasting silicon to do something that is already here. But I won't mark it down. Are we still doing okay? So the next question now is, which is not in the actual question, but I do want you guys to kind of think about it, is why do we care? Why do we care that this takes 5 clocks or 5 not 5 clocks, but 5 propagational delays? So that we know how fast we can push it. Yeah, go ahead.
I'm going to say how long you have to wait until you get the right answer.
Exactly. So from the time that all the X bits and all the Y bits and also K0 is available, how long would it take in order for the sum and the overall carry to be computed reliably? Because you don't want to store that sum any earlier than that. Is that making any sense? Okay. All right. So that's the question, and the answer is also 5 levels. But this time you definitely need to draw a picture. I need to draw a picture to see it. Are there any questions about this question? Nope. All right.
What is the total number of gates to propagate?
Yep. It'll be 5.
Level of gates.
Ah, okay. How many? Should have changed it to levels. So how many total number of levels of gates? It has to do with time, basically. What is the latency time? I'll think of a way to ask the question properly, but you have a point. But do you guys understand what I'm asking for? After I said it, okay, very good. Okay, so I'll try to think of a better way to say that.
Professor?
Yep.
The 3-bit carry look ahead, are you talking about, since you mentioned that it's the K3rd component, the third component of the carry?
The 3-bit means, the inputs are 3-bit numbers. Your sum is a 3-bit number, which means your final or your leftover carry is K3.
So we're looking to find K3.
It needs to figure out what is K3.
Right. So then would we get all the bits that we need for K2, add those to the ones that we need for K3?
No, because K2 require less time. Let's flip back to the picture here. This is K2. And the previous picture is K3. But K2 is not a final answer. K2 is only utilized internally in order to compute the bit 2 of the sum. So that's why, while K3 is the final result that we need by itself, K2 needs to have another exclusive OR gate here in order to give us the actual sum. Is that kind of...
Right, and so we have the other diagram and this diagram. And we have to go through all these, all of this before we get to the other one. So do we add this one as well as the other one?
You take the maximum of those two. The maximum. So in this case, we have 5 levels of gate propagation. In the previous one, we also have 5 levels of gate propagation. So the maximum of 5 and 5 is just 5. So that means it would take us exactly 5 gate propagation in order to go from the given bits to the result bits. Now, on the other hand, if one is taking 6 propagations and one is only taking 5 propagations, then you have to take the maximum, because I need to make sure that every single bit of the output has settled down, and that's the time that I'm trying to compute. So you're not going to add the 5 and the 5 because they're not sequential. They can be computed at the same time in parallel. Is that okay? All right. All right, so getting back to the questions. Number 8. So number 8 has to do with double conversion. So in this question, we know that a double, okay, has a bit pattern of 0xC880 and then a whole bunch of zeros. What is the value that it is representing? The first thing you need to do is to convert this back into binary. How do we go from hexadecimal to binary? I'm going to give you this table. Would that help? You take one hexadecimal digit and you convert it into the 4 bits that it represents. So that means in this case we have, let me just kind of spell this out one by one. Yep.
On the test, you're going to give us that table, right?
I will give you that hexadecimal to binary table.
I don't know if I need to copy it all down.
Well, you want to prepare your own, cheat sheet or whatever note you want to bring with you, and if you put it on your own paper, it's going to be more helpful because then you don't need to look at it, because otherwise you have a lot of flip-flopping to get to the content. So I would advise you to put this table onto your own sheets of paper so that you don't have to rely on the question itself and go back and forth in order to look up this table. Okay, so the first thing you need to do is to convert this back into a binary number. So to convert it back into a binary number, okay, I didn't do that step here. C is 1100, 8 is 1000, 8 is 1000, and then we just have zeros after that. Okay, so this is representing the binary bit pattern that is known as 0x in hexadecimal, C88, and then a whole bunch of zeros. Is that part okay? The conversion? Yep.
Are you okay with us using the ellipses if they're just
Yeah, absolutely.
zeros?
Yep. No need to write like 40 something zeros. Okay.
So
Yep.
you're saying C is okay, 1 and 2.
Yep. C is 1100. So this becomes the most significant bit, which is bit 63. Bit 63 is also known as the sign bit, so you have to tell me that this is the sign bit. The next 11 bits, okay, 1, 2, 3, this is 7, and this is 11 bits. This bunch here, which is also repeated here, is E, but E is not your actual exponent because the whole thing is offset by 1023. It's okay, we'll deal with that later. We just need to know what E is. So it is 1024, which is this one here, 120 plus 128, which is this bit here, plus 8, which is this bit here. So this 1160 or 1160 is a decimal or base 10 number. Is that okay? How we convert from 11 bits unsigned into the value that they are representing. Okay? The rest, okay, so in order to compute the actual exponent of 2, you have to offset it by 1023 because that's part of the standard. 1160 or 1160 minus 1023 is 137. That is your exponent in base 2. The rest is the mantissa or the fractional part of the mantissa. But remember, this is just a fractional part, which means there's a 1 point that is implicit. So the overall value represented is negative because of the sign, times 1 point a whole bunch of zeros, because the 1 point is implicit. The explicit bits represented here are just the fractional part, which are all these zeros, times 2 to the power of 137, which is the way we do the computation here. So this is the actual value represented by that number, by the bit pattern of 0xC88, a whole bunch of zeros. Are we doing okay so far with this, or not?
Question.
Yep.
What are the double asterisks?
The
So like
to the power of. Yep. So if I the slightly better way to do this is to use the equation minus 1 times 0,000 times 10. Oop, where's the dot? It's up there. Oh, okay, I don't want that. I want C dot, center dot, times 2 to the power of negative 137. Hmm? How's that?
Zero is really nice to do.
Huh?
The zeros or necessary?
The zeros?
The however many zeros it is, it's necessary.
Oh, you don't need all those. You can erase all of these zeros if you want. Yep, that works too.
The exponent's negative?
Yes, the exponent. Oh, the exponent is not negative.
Oh, okay.
It's just 137.
If the mantissa bits were not just all zeros, it would be the negative 1 times 2 to the power 137 times 1 point whatever the mantissa was. Or
Well, let's work out another example where they are not all zeros. Yep, go ahead.
I was going to say chance. Good.
Okay, so we'll work out another example, and I'm gonna use mousepad for that. So let's figure out what is the value represented by 0x. Okay, we need to think about this a little bit. 8. Nope, not 1. I don't want 8. I want a 4. And all zeros. Okay, so this is the bit pattern. I want to know what value is represented by a double that has this particular bit pattern. Is that okay? So we have to do the same thing. We have to look at each hexadecimal digit and spell it out as 4 individual bits. So this number is going to be 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I'm spelling out some of these because they're important, and then the rest are just all zeros. Is that okay so far? This is bit 63. Okay, so let me try my best to label it. This is 666 3210 5555 5555 5555 da da da, and this is 3210 65432, and then this is 10, and these two should be 4s, 9, 8. Okay, so I'm trying to number the bit positions with 63, so you kind of have to look at it sideways. Is that okay? Does everybody understand what I'm trying to express? So the most significant bit is bit 63, the second most significant bit is bit 62, and so on. Okay, so what is the sign of this number? The sign is a 0, which means the number is non-negative. Okay. What about E? E is pretty easy. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And in terms of base 10 number, what is that? You count the number of zeros, and then you say 2 to the power of that. So we count how many zeros? We got 10 zeros. So it is representing 2 to the power of 10. Okay. So this is 2 to the power of 10, which is 1024. Okay. What about the mantissa? The mantissa bits are all zeros, but remember these are all the fractional parts. Okay. So that means that the actual mantissa is 1 point and then followed by all zeros. Are we doing okay so far? E2, which is the actual exponent of 2, is E minus 1023 by definition, because it is offset by 1023, so that means it is just 1. Because E itself is 1024, 1024 minus 1023 is exactly 1. So the value that we are representing here is going to be, if you want to emphasize, you can use a plus, but if you don't want to emphasize, not leaving out the sign is implicitly non-negative. This is 1 times 2 to the power of 1. So that would just be 2. It's exactly 2. Are we doing okay so far with the derivation? Is that okay or not? Okay. So the question now is, when you're studying and you're saying, okay, I think I got this down, but how do I check that my answer is actually correct? Do you guys remember the Gdp trick that I used in class? No, not really. Well, that's why I videotape everything. You guys can actually watch watch the lecture when we first started to talk about floating, double precision floating point numbers, and you will see the GDP trick. I'm going to do it again. It's really easy, so it doesn't take much time to explain it. Okay, so the first thing you do is you make a very simple program. Oops. There we go. And you want to make sure that you're dealing with 64-bit integers. So it is really helpful to pound include stdint standard integer.h. And in here, you just have to say uint 64 underscore t, which is a 64-bit unsigned number. Whether it's signed or not really doesn't matter one way or another. And you just call it d, and then you say d equals to 0. You have to initialize it not to get it optimized out of the program. Return 0. This is the entire program. And then what you do is you use GCC, compile with debug option, -o main, to name the executable main itself. You can always change the executable's name. And then we want warn all just in case. Oops, I need to tell what program to compile. This is C. This is main.c. So it's all working. Then you go to GDB main, put a breakpoint on line 7. Run the program. The program itself doesn't do anything useful. Okay, so what you do is then you say set var d equals to whatever number that you want to play with, and we can just play with the other one, which is 4, and then followed by a whole bunch of zeros. I'm gonna throw a 1 into this whole thing here. This is a bit of 1, and then we'll have a whole bunch of zeros after that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So this is not exactly the same as the other one. It just has one other bit that is set to a 1. So now the question now is, what is that 8 corresponding? Because that's the only difference compared to the example that we just looked at. And how would that change the value that is represented by this particular double? What do you think? Where is that 8 going to? Which bit is corresponding to the 8? There's a single bit. Okay, so the 4 is it will be bit
First bit of the mantissa.
Aha, very good. Okay, so it's the first bit of the fractional part of the mantissa is a 1. So that means the actual mantissa is 1.1 times 2 to the power of 1. So what is 1.1 in binary? We know what 1.1 is in decimal. It's 1 and 1/10, right? How did you get 1/10? How did that 10 come from? Base 10. So 1.1 in base 2 is 1 and 1/2. Okay? 1 and 1/2 times 2 is 3. So this really should be representing the value of 3 when it is interpreted as a double. Is that okay? Sort of? Okay? So we want to now play that other trick and say print dereference, casting the address of D into the address of a double, and then dereference it. That is exactly 3. Are we kind of doing okay so far with this? Maybe. Knowing that this bit pattern is 3, how do I make it 6? 6 is 3 times 2. There's a reason why I make it 3 times 2, because times 2 means we just have to modify the exponent. We have to increase the exponent by 1. So when we go back to the set var, how do we change this bit pattern so that the exponent is now 1 more than what it used to be?
Change the 405.
Nope, that will change it a lot because remember, you're changing the more significant bits when you change for the 4 to a 5. You don't need to do all that. The least significant bit of E is which digit? Which digit contains the least significant bit of E? It's this particular 0 here. So I need to up it from 0 to 1. Okay. And then we do the print again, and this time we should say 6. Say that one more time.
The 8 remains after the 1. I mean, just be 4, 0, 1, 0, 0.
No, this has to be an 8 because we still need the mantissa to be 1.1 followed by all zeros. It's 1.1 because it's 1 and 1/2. So 1.1 and 1/2 times 4 in this case is 6. Is that okay? How do we change this 6 to 7? I need to change only one digit of the hexadecimal number, but how should I change it? First of all, which one should I change? Let's go through the hexadecimal digits one by one, and we'll see, okay, which one contains the bit that we want to change. First of all, when we're changing from 6 to 7, are we crossing a power of 2 boundary? No, they're both less than 8 and greater than or equal to 4, so we are not crossing the boundary of a power of 2, which means we do not need to change the exponent. Is that okay? Do they have the same sign, 6 and 7? They have the same sign, so we don't need to change the sign bit either. So that means the first or the most significant 12 bits, 4, 0, and 1, do not need to be changed. So we know that we need to only change the fractional part of the mantissa. So now the question is, if it is 7, how do we express 7 as 1 point blah 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 times some power of 2? We know the power of 2 already, don't we? Because we are keeping it. Okay, the power of 2 is actually 2. So what times 4 is 7? It's 7 over no. Okay, so it's 7. It is correct. Okay, I stand corrected. 7 divided by 4, but 7 divided by 4 is what? Okay, let me switch to this part here. Okay, turn to a new page. Okay. So you're dealing with 7 divided by 4, which we already know is, it's 1 3/4. The question now is, when you know this as a decimal number as 1 3/4, how do you express it as 1 plus some power, some fraction that has 2 to the power of 1 as the bottom, as the denominator, and something like that? Possibly this and that, and so on. Okay, because those are the numbers, those are the digits to the right-hand side of the decimal point or the binary point. So what do you think? How do I fill in the blanks here? 1 here, and a 1 here.
1 here.
And then all zeros here.
Yeah.
Yep, okay. What is this bit? What is this 1 going into? Which bit position are we talking about?
Most significant bit of the 8 in the hex, right?
Right, this is bit 51. This is bit 50. Is that okay? So getting back to GDB, that is corresponding, the 8 is already here. The 8 is accounting for bit 51. So we have to add 4 to the 8 because of bit 50.
B?
No, you're off by 1. C.
Oh,
Yep.
okay.
C is correct. Okay. So we have to change bar and change this to a C because we want the bit that is just less significant to the bit corresponding to that 8 to also be here. And then we print, now we get 7. If I want to change it from 7 to 8, we got a few changes to make. Because when you change from 7 to 8, it is crossing that boundary of moving on to the next power of 2. So that means you have to adjust the exponent, but remove everything in the mantissa. Because 8 is 1 itself times 2 to the power of 3. So you have to represent that 3 as 1026 because it's offset by 1023, but you leave the mantissa completely empty as the zeros. Is that okay? Sort of? Yep.
You use the last number, the one that you put the C to actually find for the E and just to see, because you keep on saying that the 1 is the exponent, right?
Nope, the 1 is a part of the exponent.
Part of the exponent.
Yes.
Why? 1 is before the fractional part, right?
Yes.
Why is the fractional part after the exponent, but the 1 is before the 8, which is part of the fractional part?
Okay, so let me see if this will help. So I'm going to move this all the way to the top, and then we'll discuss this in a, okay, this is great. We got bit 63, 62, 61, 60. This is the sign bit. And then we got bit 59, 58, 57, 56. And then we have 55, 54, 53, 52, 51, 50, 49, 48, and so on. Okay. This is the sign bit all by itself. It is just standing on its own. It is the most significant bit. And then the next 11 bits, which is this bunch here, this is E, which is the offset exponent of 2. It is not the actual exponent of 2, but this is offset by 1023 already. The rest is the fractional part of the mantissa. I'm going to name this one as M1, M2, M3, M4, and so on. So when you look at the value this is representing, the sign is clear what it is representing, so I'm not too worried about it. These would be like 1 point in binary, M1, M2, M3, M4, and so on, times 2 to the power of E minus 1023. That is the value being represented. Is that okay? Because this way I'm just chopping the number into the individual bits, and then we are grouping those individual bits back into the portions that we need in order to figure out the value represented by the bit pattern. Is that okay? So in the example, in the 401C, in this particular example, the 4 would be these 4 bits. So a 4 is a 0, 1, 0, 0, and then the 0 would be these 4 zeros, okay? 0, 0, 0, 0. The 1 is representing these 4 bits, which is 0, 0, 0, 1, and then the 8, or the C, okay, let's use C here. The C is having a 1, 1, 0, 0 here. So this is corresponding to this example here in GDP. Result, we know the sign is a 0. We also know that 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 is E. But that's just 1024 plus 1, which is 1025. But 1025 is offset by 1023, which means the actual exponent of 2 is just 2. And then these 2 bits, 1, 1, is the beginning of the fractional part of the mantissa. So it's 1.11 as a binary number. But the first one to the right-hand side of the point is representing the number of halves, and then the next one is representing the number of quarters, and then 8ths, 16ths, and so on. So that's how we can figure out that, oh, that's just that's just 7, because 1.11 is 7 divided by 4, and then when you times 4 with that, you get 7 back. Is that okay? So I can ask you a question that is the other way around. I can give you a pattern in hexadecimal and ask you what value it is representing, or I can ask you, this is the value that I want to represent. How do we do it? Okay, which kind of is answered here too, because I'm tweaking the hexadecimal representation depending on what value we want it to represent. Yep.
The stream is working.
I sure hope so. It's streaming, and it's streaming the right content, and the voice is going to. The most sure way to double check is to use your phone, go to YouTube, and try to watch it, see if everything is working. So are we doing okay so far with the floating point number representation? Okay. So this kind of brings us to your homework assignment as well. Okay, so you're doing two things. You're studying for the test and working on the homework assignment, but they are closely related, so I don't think it's extra work per se. So your homework assignment is already here. It's called double conversion. And I give you this program as a starting point. So you're in a double conversion homework assignment, you start with that particular program, and your job is to implement the function called convert to double. I give you my base 10 conversion thing, not the base 10 conversion, but the base 10 parsing subroutine, so you can start with that. So your job is to convert a scientific notation in base 10 into a double representation. The pseudocode is already in the notes. Okay, let me show you where you can find that notes. Of course, I do kind of hope that you guys know where to find it already, because we have been talking about it for some time. But in case you don't remember, this is where you can find the notes. And the pseudocode is section 5. Section 1 probably is done already, so forget about section 5.1. Section 5.2 is where you start. Okay, so section 5.2 is where you start, and then you go through all this. Some of the math you don't have to worry about. This is already done for you. This is one loop. 5.2.1 is one loop. 5.2.2 is another loop. After everything is done, you have to do the normalization, which is also loops here. And then you have to do the shifting of the binary point, but that is not, it's not done by a loop, it is just by modifying the E. Okay, we're just doing some calculation with the E. Computing the E means we just need to do the offset by 1023. And then 5.5 is just using bit shifting and also bitwise OR in order to combine all of these components back into one single thing. So the pseudocode is here, okay? I just did not spell it out, using pseudocode. But whenever you see as long as, it's a while loop. And then you have conditional statements, if blah, 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 do this, if blah, 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 do that. So are we doing okay so far with this? So when you're studying for this test and debugging your program, you are really reinforcing your understanding of the double representation, because that's basically what it is. We're just converting how we represent a value from base 10 to base 2 and then to the double representation. Any questions about the homework assignment? No? Okay. How would you, yeah, go ahead.
It's about the previous homework assignment, so if we're going to talk about other stuff, it can wait. I can wait if you're going to talk about other stuff, because it's about when I turned in the parsing, I took out your L1 label and put in stuff for me just to debug. I forgot to put the L1 back. Are you grading specifically on that L1 label?
Yes, the script will be looking for L1.
Okay, so I messed up then.
So you might want to leave a note.
Well, I already turned it in. It turned it in on the due date. But
okay.
I was just wondering. It's cool.
I will probably find it and fix it, but I will take some really token points off
I understand
because of that.
A bunch of stuff. Just go through it, but
okay.
I was just curious.
No problem.
Thank you.
Yeah, just don't do it in the new program.
No,
leave L1 alone.
I turned it in, and then when the next day I went, crap, so I already switched it. It's already back to normal on my computer.
Okay, not a problem. So are there any questions about the midterm or the first exam? It's going to be next Monday. Yep, go ahead.
So there won't be any questions other than the ones there won't be anything outside what we covered today, in a sense, there won't be any other concepts that weren't going to be on the exam that we haven't looked at.
In terms of concepts, it will be everything from the beginning of the semester up to and including the double representation. Unless I specifically say that it will not be in the exam. Like all the discussion about Turing machines and whatnot, that would not be in the test. Yep.
There's one question we didn't go over, but it's the other way around.
Did I miss one?
We only have like 2 minutes, right?
We got 2 minutes. I think that one is very similar to this one.
Binary data.
Oh, how do we represent the value of 5 as a double? Which we kind of went over already because we just went from 1 to 2, and then 2 to 3, 3 to 6, 6 to 7. So we basically got it covered as well, just in a slightly different way. Okay, but this is a really, to me, this is a really interesting way to kind of play with it, is not to try out something that is really hard to represent. I wouldn't try like 23 or something, like that. Just try something easy, okay? 17 would be a good one, because 17 is 16 plus 1, okay? Very easy to look at. The big pattern should be fairly clear, easy to work with. And also the power of 2 is not crazy, because it is just, the power of 2 should be 4 in this case. So you're expecting E2 to be 4, which means E should be 1027. And you can convert it into binary, convert the whole thing into hexadecimal, throw it in here, test it, make sure that it works. Is that okay so far? Okay. Now I'll just do this one last thing before we leave, in the lecture. You can do this in a different way. What you can also do is to set var, but this time do not use D, and then you use the casting, so that this time you can store a double number into the 64-bit integer, and then you examine the actual bit pattern of that thing. Is that okay? Let's try it. 16, easy one, right? Then you can say print /x D. Okay. It looks like it's pretty simple, but does it make sense to you? This 4 is the most significant bit of E. This 3 is corresponding to the least significant bits of E. So your E is really 1 followed by a bunch of zeros and then 1, 1 at the very end. Is that okay? That will be 1024 plus 2 plus 1, which is 1027. But remember, this whole thing is offset by 1023. So 1027 minus 1023 is 4. That is your actual exponent of 2. 2 to the power of 4. What about your mantissa? They're all zeros. The fractional part of the mantissa is all 0, which means you're dealing with a mantissa of 1 point, all zeros. It's just 1 itself. So it becomes 1 times 2 to the power of 4, which turns out to be 16. That's exactly what it is. If you want something crazy because you've got nothing else to do, try 0.3 or just 1.3. Okay? You might think, oh, 1.3, easy peasy. We might see a few digits turning from zeros to something other than 0. That's not the case. Because it's almost the same thing as asking you to represent 1 1/3 as a base 10 number. It cannot be done with a finite number of digits. Okay? But some numbers are easy. 1.25 is very easy because 0.25 is a quarter. A quarter is a proper power of 2. So when you look at this number, it's very clean. Is that okay? 125 is easy to deal with. That is easy to deal with because that's just, I think, 7/8. So anything that has a denominator that is a power of 2 is easy to deal with. But if you have anything that it has a denominator that is not a power of 2, it can be a multiple of 2. Doesn't help. Okay, it has to be a power of 2. So this number is really easy to deal with. It has one more digit, I think. That's it. So that's still pretty easy. All right. So we're doing okay so far with this stuff. Okay. So the more you play with this, the more you'll get some insight, of how this whole thing works. And don't just repeat the experiments. Use new values to test it.
This is due Monday or Tuesday, or? Every Monday or
The
Wednesday?
homework itself is also due on Monday,
Okay.
which is the day when we have the exam. Alrighty, so we're going to move on to the lab, and I will see if I can help you guys do the homework, explain the concepts.